This is 3.2.3, refraction at a plane surface. So as you guys know from GCSE, refraction occurs when light passes from one medium to another. Light slows down and changes direction. So the first question that we answer is why refraction happens, and that is because light slows down when it's traveling through a transparent medium. Put a box around that. So we'll sketch this very quickly. So we'll draw a boundary. We will do air on this side and glass on this side. If we have light passing through in a straight line, I'll sketch the waves of this light in terms of its wave fronts. And I'll try to draw them as equidistant as I possibly can. So, when traveling from air to glass, these wave fronts, they represent, you could say, for example, a crest in a wave. So each of these lines represent a crest. Now, if it passes from air to glass, the frequency of the wave does not change. So the wave still oscillates at the same frequency. So it still takes the same amount of time to do a single oscillation. But the wave slows down. So how much distance is covered per oscillation now? Is it going to be greater? Is it going to be less? It's going to be less. So what we'll observe that to be is a shortening of the wavelength. So these lines now become closer together. So in this situation, the light does not refract because it's come at right angles to the surface or to the boundary between the mediums. But what we can see is that the frequency of the light remains constant. And so if frequency is constant, that's equal to C over lambda. So both of these must change. So both the speed decreases and the wavelength of light also decreases. When trying to describe why or how light bends, we can imagine that each wave front is a line of soldiers, or we can imagine that each wave front is the axle to two wheels. So you can imagine it as a car. If you look at two wave fronts, The wavefront in front represents the axle for the front wheels. The wavefront at the back can represent the axles for the back wheel. And moving from a less optically dense material to a more optically dense material, for example, air to glass, is like moving from driving on tarmac to driving in mud. So let's sketch that and we'll talk about it as we go along. Imagine each wavefront as a row of soldiers. So if we did our air glass boundary again, and we had it entering at some angle, okay, we're about to reach the boundary now. When we reach the boundary, if you imagine that you're walking in the same direction as these soldiers, do the soldiers on the left side or the right side enter the mud first? Soldiers on the right side enter the mud first. If you look at that final line, the right side of that line is about to enter the glass. The left side of that line will continue to remain in the air. So if I draw the next line, half of it remains in the air. The next half has already entered the glass. In the glass, however, they're going to move slower. So they're not going to move as far. So we're going to have these soldiers moving less. So if we carry that line over, we get a line that looks like this. And then by that time, all of those soldiers have already transferred from one medium to the next. And the lines should now be closer together. Like so. So you can think about it as wheels as well. The right wheel of that front axle will enter the mud first. So the right wheel will slow down first while the left wheel is still moving faster. That will cause the car to rotate. If two wheels at the front are not moving at the same speed, the faster wheel will cause the car to rotate to face in the other direction. So if your left wheel is faster, you will turn to the right. If your right wheel is faster, you will turn to the left. So at this point is where we have a slowing down, causing a change in direction. Let's start a new page. So we'll move over to doing these as ray diagrams. When we're drawing our ray diagrams, we need an imaginary line called the normal. And we draw the normal perpendicular to the surface of the boundary. So this is the normal line, and it's perpendicular to boundary. This side is glass. This side is air. So if we drew our two lines, we get something which looks like this. We draw our angles, not from the ray to the boundary, to the material itself. We draw the angles from the ray to the normal, the imaginary line. So this here is our angle of incidence, so we could call that theta I. And this is our angle of refraction, we call that theta R. All angles are measured from the normal. And so we look at another material property called the refractive index. And the refractive index is simply a ratio between the speed of light in a vacuum and the speed of light within that medium. So let's write this down. The refractive index is the ratio of the speed of light in a vacuum to the speed of light in the substance. So for that, we'll do N equals to C over CS. Put a box around that. N is the refractive index. Refractive index has no units. C is the speed of light, which is equal to 3 times 10 to the 8 meters per second. And CS is speed of light in the substance. Which is measured in meters per second. So for example, if glass has a refractive index of about 1.5 or 1.3, can't remember which one it is. Let's just assume it's about 1.3. That means that the speed of light in a vacuum is 1.3 times faster than speed of light in that substance. And so we can talk about Snell's law, which is that N1 sine theta 1 is equal to N2 sine theta 2. That's when light is traveling from one material to another, or one medium to another. You do the refractive index of 1 multiplied by the angle of incidence, sine angle of incidence, and that's equal to the refractive index of the other one multiplied by sine of the angle of refraction. And in air, the refractive index is approx 1, or approximately the same as a vacuum. Okay, let's start a new page. Next, we'll talk about total internal reflection. So we'll draw a boundary. Now take note that I'm drawing my boundary horizontal this time rather than vertical. And we'll sketch our normal line. So we have light, which is trying to now move from a more optically dense material into a less optically dense one. So at the bottom here could, for example, be water. And at the top will be air. And in water, light moves slow. In air, it moves fast. So here we've got some angle of incidence, and over here we've got some angle of refraction. And this angle of refraction is almost perpendicular, it's almost 90 degrees. So if we were to then increase the angle of incidence further, we will at one point reach something called the critical angle. At the critical angle, the light ray will travel perpendicular to the surface, so to that boundary. So increasing the angle of incidence will reach the critical angle theta c. I'm just going to change color of my ray at this point so that it becomes easier to see and understand. So this now is called the critical angle, and this becomes 90 degrees. And again, we've got water at the bottom, air at the top. So, if we look at what's happening in this situation, you start with n1 sine theta 1 equals to n2 sine theta 2. When you reach something called the critical angle, you've got n1 sine theta critical is equal to n2 sine 90. Sine of 90 is equal to 1. So the equation becomes sine theta critical is equal to n2 over n1. Put a box around that. Now, we have to look at the equation and realize that there are some limits to this. If sine theta critical is equal to n2 over n1, then n1 must be larger than n2. Because if n2 is larger than n1, then you get a number which is larger than 1. And if you do the inverse sine of a number larger than 1, what do you get? You get an error. Because sine theta has a range of 1 to minus 1. So you cannot have a number being entered into inverse sine that has a magnitude greater than 1, whether it's positive or negative. So the condition here is that n1 is larger than or equal to, in fact I'll get rid of the or equal to, is larger than n2. If we increase the angle of incidence even further after that point, then we get a phenomenon called total internal reflection. So we'll sketch what that looks like. We'll draw our water-air boundary again. We'll do our normal again. And we will increase the angle further. And that results in a reflection. So we've got air, water, angle of incidence, and then it becomes angle of reflection rather than total, angle of refraction. So here, this is total internal reflection. We can do an example of this. So example, calculate the critical angle for light traveling between a glass water boundary N glass is equal to 1.5, N water is equal to 1.3. Pause the video here to attempt the question and play the video when you're ready to see the solutions. So, to answer this question, first you need to know that for the critical angle, or for total internal reflection to occur, the ray of light must be trying to travel from a more optically dense material to a less optically dense one. So that means that the direction of light has to be from glass to water. So we write the equation sine theta critical is equal to n water over n glass. We put our values in, so that's 1.3 over 1.5. Next, we need to take the inverse sine of that. So theta critical is equal to inverse sine 1.3 over 1.5. If you put that into your calculator and let me know what the value is. 61 degrees. And that's the end of part 1 of 3.2.3.